So today I'm going to, as the keynote, one of the keynote speakers, keep this talk to a relatively high level, and I hope this talk challenges you, inspires you for subsequent discussions for the next few days. I'm going to touch on at least my view of the definition of open ocean versus offshore. I'm going to do a brief timeline of aquaculture, and then I'm going to walk through some of the cutting edge technology our company and some other companies are working on, and then finally leave you with some final thoughts on what we think are the critical success factors of an open ocean fish farm. Oops, wrong one. Here we go. So we've been using the term offshore for years. I challenge us to use the term open ocean, and let me explain why. So these are our clients in Panama. They truly are open ocean. They're also 12 kilometers offshore. Every day, except for most of the year, except for about 2 to 3 months, they experience 1.5 to 2 meter waves every day. And there have been measured significant wave heights of 5.5 meters. Actually, we're starting another project off the east coast of South America right now, which is about 40 kilometers offshore in the open ocean that has similar wave environments. So that's an example of open ocean. We also have clients in Hawaii on the Big Island, Blue Ocean Mariculture. They're only about 0.5 kilometer offshore. They're also open ocean. They have actually a 6,100 kilometer fetch to Japan. So even though they're only 0.5 kilometer offshore, they face some pretty challenging environment as well. They have strong, unpredictable ocean currents that come from the gyres. They also have a vertical lava beach only 600 meters away. So you get wave reflections coming back and you have very confused chop. So again, I encourage you to use the word open ocean rather than offshore. Offshore has a prejudice that it can be distance. I'd like to introduce a new term that we're starting to use at our company, InnovaSea, and we call it duck and cover. Here's an example of one of our clients in La Paz, Mexico, in Baja Sur. They're in the Bay of La Paz. It's about a 40 kilometer fetch over to the other side of the bay. About 95% of the time, it's very, very calm. But then they do have some pretty ferocious storms called El Nortes, where traditional equipment would not survive. So we've developed a third cage. A lot of you are familiar with our sea station and our aquaspar. But a third cage we call duck and cover, which is very similar to the more traditional pens with walkways. But we spent a lot of time and effort designing the buoyancy system so that it sinks in a controlled manner, rises in a controlled manner to eliminate barotrauma, and also does not go down like this or potato chip. So those are sort of our definitions of open ocean, offshore, near shore, and so forth. Now, I'd like to go to the topic of this conversation on the history of aquaculture, and I'm going to refer to a good friend and retired colleague of mine, Dr. John Forster. For those of you who don't know him, he was responsible for bringing salmon to North America. About 10 years ago in New Orleans at a conference similar to this, he used an analogy of the age of flight to the development of aquaculture. And he started off with Da Vinci and the concept of flight and equated it to the Egyptians and the Chinese about 4,000 to 2,000 before Common Era with carp and tilapia. And so, big deal. So we all know that that's the start of aquaculture. But he said 10 years ago that aquaculture then, about 10 years ago, was no more technologically advanced than the Wright brothers and the first flight, with the traditional salmon pens. I'm not quite sure I agree with him, but let's continue with his theory. And I would say, actually, we are at the point of commercial aviation with wide-body jets. We now can safely get people across the ocean on a regular basis. These types of pens, sea stations, I don't see Darko in the audience yet, but he has a tension leg cage. that enables farmers to go into the open ocean on a safe, regular basis. Much like there are trials and tribulations of crossing the ocean in a plane, we now have equipment where you can produce a farm, for instance, Open Blue is about 1,200 tons now on one site. They have plans in the next 2 to 3 years to get up to 3,000 tons on a site that has about 600 kilometer fetch. The next island is Jamaica, with waves of 1.5 to 5 meters tall. So where do we go from here? So I'm going to tell you about the next stage of flight and also technology. What I'm going to do is I'm going to walk you through the equipment that we and some of our other colleagues in industries have been able to produce. And I'm going to use this background of an open ocean fish farm. Is that? Yeah, I thought that was Darko. Just came in, just missed his cue. It's not. Anyway, here's a typical open ocean fish farm. I'm going to start off with the operations that we do. So feeding, grid-wide feeding, big deal. We see it on all the farms now. The difference now with open ocean is most of these pens are submerged. And if we're going to feed submerged, we have to deliver through water. We cannot use it through air. We can't pump air through the hoses and then have the bubbles come out and scare the fish. So we have developed an inline feeding where we introduce the feed into the water and then pump it. And we can reach any pen in the grid system in 90 seconds, which is critical when pellets start losing their nutrition. They start leaching out when they're water too long. We also have touchscreen controls, which can also ultimately get sent back to shore. Once it gets into the pen, water attenuates, the jet stops very quickly, so we have to disperse it amongst the whole cage. So we've developed, it's essentially a soaker holes with hundreds and hundreds of specially shaped holes and specially shaped holes to distribute the feed throughout the cage and allow the smaller fish to eat it. Mortality removal, the unique conical shape of the net allows all the dead fish, we hopefully don't have too many, but they go to the bottom of the cage, they get caught underneath these baffles, because in warm water, dead fish only remain negatively buoyant for a few hours before they come up. It's important, specifically in the Caribbean and so much in Hawaii as well, that you keep your dead fish contained because sharks will come quite quickly. So they remain in that chamber until they are airlifted out to a mortality barge. Again, diver free. Harvesting, with these particular cages, you can do about 95 to 98% of the harvest diver free. Once you install this net, you sink the cage, the fish are attracted into that net, you raise the cage up, and you harvest the fish out with a pump to the boat. Truth be told, to get the last 5 to 3% out, you do need to put a seine in, but you can do that when the weather is slightly calmer. But you have the ability to harvest in almost any weather to meet your production deadlines. It's difficult to see, but we use ROVs on sites. Typically, these sites are about 60 meters deep or more. So beyond the depths of your normal standard, non-deep sea diving or nitrox diving. Here we have an example. We've just dropped an anchor. We want to make sure the chain is not tangled before we set it. So it's imperative that you have a good ROV pilot and a good maintenance program on an open ocean farm. Cameras. We're working hard on developing a camera suitable for this environment. Right now, there are two types of cameras available on the market. The very expensive, cost-prohibitive ones that are meant for the North Sea at 900 meters, and then the ones that are for sheltered sites. We've tried those ad nauseum in both Hawaii, Panama, Mexico, Spain, and they don't last more than a few months before the wires break. So what we're working hard on is a low-cost camera and camera housing that's suitable for those environments, but it's not cost-prohibitive. We're also working for going from analog to digital. So we're getting rid of analog video feed, going to digital for easier transfer of data, analysis, and so forth, and I'll tell you why. So we're using digital data. It's difficult to see, but we're working with software developers to work on pellet detection through the fishbowl. Obviously, FCRs or food conversion ratios are critical to your bottom line. 60% sometimes of your operating cost is feed. You want to make sure you are not overfeeding or underfeeding your fish. So with those low cost but efficient digital cameras, we're capturing the feed data and working on algorithms to identify that. So it can almost be a machine loop that turns it off. We have sensors, environmental sensors. In fact, I see one farmer in here who's using our products. Right now, I could pull out my iPhone and tell you exactly what the salinity, temperature, tilt, everything else is on our customers' farms. They're throughout the farm. We have sensors upstream that can tell the water quality coming into the site, sensors downstream that tell you if there's anything above background level, and within the cage, what the fish are experiencing right now. You will notice, other than the straps to hold it on, this is not a data cable, this is just a rope. It's all wireless. And we also have load cells built into the mooring lines. So in a storm, you can look back at the data or look at it in real time to see if your mooring lines have exceeded the safe working load, but obviously before it breaks. Also, if you see a dip in tension, you know your anchors have moved. So during and after a storm, we can analyze that and say, okay, we've got to go look at anchor leg number 2 or 3. Again, all wireless here. Acoustic Doppler current profilers, ADCPs. We typically have one on the floor looking up for current and wave, and also one under the communication buoy to transmit real-time data of what's happening at the site, so the operations manager can make a decision that morning as to what to bring out. All those signals are signals are transmitted acoustically to a sub-hub. And this is a company we just acquired recently called Real-Time Aquaculture. And all these sensors transmit all this data wirelessly to a submerged hub, up into a buoy above, then beamed on shore, and then onto the internet with user interfaces that you can really run off your phone or a tablet. A couple of ways we transmit to shore. We have an antenna from either a feed barge or a harvest barge transmitting to shore. Here in Panama, we have the top of an ice-making machine silo receiving antenna. We also have a data buoy that has the ADCP in the bottom that transmits as well. That's not a small challenge when your buoy is going back and forth. So that was one of our biggest development challenges, is to overcome, send a strong signal back to a fixed antenna on shore 12 to 13 kilometers away. We now have a pretty strong success rate of the data. We're up to 98, 99% of all the data being transferred in some pretty heavy seas. Closing up here, this is a shot of the pens in Hawaii, another technology that we have implemented into our product line, and it's now sort of taken over. There's really no other options that people are asking for, and that's copper alloy mesh. What you're looking at now are fish pens in Hawaii that have been in the water for about 9 to 10 months, judging by the size of those fish. That pen has never been cleaned. Shark attacks are down to 0. Dolphin attacks are down to 0. Monk seal attacks are down to 0. Those were the predators there. Before they put in copper alloy mesh, the farm was spending $5,000 to $8,000 a month per pen on hydrogen peroxide treatments to knock down the trematodes, which are gill flukes and skin flukes. The eggs tend to aggregate on fouled netting. They've got a little tail or a flagellum. They all hatch at the same time. The new larvae latch onto the fish, they get itchy, they scratch themselves, and they get sick from Vibrio and other things. So if you can knock out the trematodes, you're saving a lot of money. the ROI for the farmer, the difference between that and traditional netting is about 1.5 harvests. So eliminating the predation, the trematodes and so forth. The other nice thing is this material is 100% recyclable. I had a conversation with one of the delegates about carbon footprint and life cycle analysis. This has a very, very low carbon footprint because you don't need the fuels to clean the net. It doesn't go onto the town dump. It goes back to the original provider, melted down and made into new net. And finally, you get a financial return on it. They give you a refund for the raw material that you give back. I want to close up on some critical success factors for open ocean farms. First of all, capital. When you start a new venture, and there are not a lot of new farmers here, but this is some advice we give to everyone, and only about 20% listen to it. You cannot go into open ocean aquaculture undercapitalized. You are going to have to pay your school fees. There are going to be unknowns. You need to have working capital. You want to be able to address a $10,000 problem on Friday afternoon or Saturday morning and not face $1 million problem on Monday. Site selection. Too often we have enthusiastic clients who come to us and say the good news is we have our permits. The bad news, it's either too shallow or it's in conflict with other stakeholders and that sort of thing. So I encourage new farmers to reach out to folks with GIS capability. There are consultants out there, a lot of us and our competitors do it before you commit resources. Species selection, make sure you do your homework on the front end and the back end. Hatchery technology for a new species can be very expensive and very time consuming, all the iterations that you have to do. And you also have to make sure you can sell that fish. It costs a lot of money to introduce a new fish to market. Our clients in Panama, cobia, outside of Florida, South Carolina, the southeast United States, not a lot of people had heard of it. They've done a masterful job on introducing cobia to the American market, but it did cost them quite a penny. Staffing and skilled people, this is always a challenge, specifically for open ocean aquaculture. We tend to be in more remote areas. Once people start thinking about families and so forth, we see a high turnover in staff. So you have to make sure that you provide them with a high quality of life if you're going to retain those people. Also, those people are your eyes, ears, fingertips, so forth in there, and they can detect problems earlier on. Do not skimp on skilled staff. Feed supply, cannot stress enough that you need to have a high quality goods feed supply. Case in point, we have two customers in Hawaii. One was in Oahu and the other one was on the Big Island, and there was a longshoreman shipping strike that cut off the whole west coast to shipping, and they were without feed. Luckily, the farm on Oahu had an excess of feed and shared the feed with their competitor. But you do need to think of these. You need to feed your family, you do need to feed your fish. Fish health, you do not want to be looking through the phone book when your fish start acting strangely. You need to have excellent fish health staff on site and also those on retainer. You need to address those issues before they become expensive. And finally, systems and processes. I travel around the world going to different fish farms. I've never seen consistent biosecurity. I've never seen, consistent around the world. Some farms excel in data collection and others are lacking in biosecurity, everything else. It's very, very important to get your staff ingrained on disciplined systems, processes, so you can keep your costs low and also address problems. Now, I'd like to leave, it's difficult to see, but that's a Sea Station 8,000 cubic meter pen filled with Seriola rivoliani in Hawaii, ready for harvest with almost no mortality. So, thank you very much.